All righty. Well, hello. And if you are joining us from our last session, great to see you again. And if you're joining us for the first time today, then welcome. Welcome to the second webinar session of day two of the 2025 AMS Weather Band Jamposium. This session is Getting the Most from Your Home Weather Station with John Horrell, Michelle Storm, Rich Clark, and our moderator, Ted Best. Now, before we begin today, I would, of course, like to address some of the guidelines for our webinar. If you have questions during the webinar, please put them in the YouTube chat that should be visible to the right of your viewing screen on your YouTube page. We will have dedicated time for audience questions after the presentation, but of course, as questions arise, if they fit in with the flow of the program, we'll address them then and there. Additionally, all communications should be appropriate for a professional audience that includes individuals from diverse backgrounds. So please be inclusive and respectful in your interactions. Now I'd like to introduce today's presenters. So thank you, John, Michelle, Rich, and Ted for joining us. Ted Best, our moderator, is a lifelong weather enthusiast who enjoys volunteering and writing. He has served as a Skywarn storm spotter, ham radio Skywarn coordinator at KD5JEO, and a Kokoraz volunteer observer. He has been an associate member of the AMS since 2002 and was a member of the North Texas local chapter while living in Texas. His weather interests include severe storms, mesoscale convective systems, and Alberta clippers, a result of moving to Minnesota. And with that being said, Ted, I hand over the program to you.
You're muted, Ted.
Well, thanks very much. I'll start over. Thanks very much, Gideon, and welcome everyone. Thanks for joining our session here. We're really excited today to talk about weather stations. And, that's one thing I would add on to that introduction is that I am also a weather station operator and I'm learning. I've actually learned some things from these people just from doing this session and organizing this session. So I think you're all going to really enjoy the information and the insights that we get throughout this session today. So what we're going to do is we're going to talk about three parts of weather stations that we often look at: the instruments themselves that we use, the sighting, how to sight those instruments, and then the data. What do we do with that? How do we navigate the many ways that we can share our data? And so we have Michelle here, Michelle Storm, to talk to us about the instruments. We have Dr. Richard Clark here to talk with us about the sighting, and then Dr. John Horrell here to talk with us about the data and the navigating that world. So let's get started. I wanted to mention also, yesterday we talked about our temperatures and our weather a little bit. And today on my weather station, I was down in we were in the low to mid 40s. We're actually on our way down now. We just had a passing of an Alberta clipper. We're on the back side of that now. We're getting some really strong winds. My weather station has actually recorded some 43-mile-an-hour gusts now this morning. So again, just one of those things that we see with our weather stations makes it really easy to kind of watch the world around us and kind of fun to keep track of that. So let me go to our first speaker, who's going to talk to us about the world of weather instruments, and that is Michelle Storm, aka Michelle Spencer. You'll see her name on some of the literature as Spencer. She went and got married on us. And she is currently pursuing her PhD in meteorology at the University of Oklahoma, where she's investigating boundary layer interactions around Houston, Texas, and how the sea breeze and air pollution may affect convection initiation surrounding the city. Prior to OU, she received her MS in atmospheric science from the University of Wisconsin in Milwaukee, where she conducted a modeling study investigating forecast uncertainty in severe weather environments in the southeastern United States relating to sea surface temperature sensitivities. She earned her bachelor in meteorology from the Metropolitan State University of Denver. Michelle currently serves as the chair of the AMS Measurements Committee, and that's what brought her here to us today. This involves organizing annual symposia, holding monthly meetings, and public outreach. Michelle says that it has been a great way to connect with the weather community, and she truly enjoys the position and all that comes with it. Outside of work, she loves being in the outdoors. Some of her favorite things are camping, hiking, kayaking, and photography. She also has a cat named Ero, I think I'm pronouncing that right, who makes her smile every day. And that's great. Thank you very much for being here with us today, Michelle. And she comes to us well qualified, being the chair of the AMS Measurements Committee. Michelle, tell us a little bit at the start here about what got you into that.
Yeah, so I actually joined the AMS committee back when I was an undergraduate student. At the time, one of my professors from MSU was the vice chair of the committee, and he had an opening for a student option or a student position. So I joined back in 2018, I believe, and have gone through the roller coaster of a lot of turnover in the committee, but we have grown in size and scope in the last few years, and I am super happy. And we have a great team of folks from all different parts of the instrument measurements and observations community.
Well, that's great. Well, we welcome you here today. We're so glad to have you with us. And without further ado, go ahead and take it away and talk to us about meteorological instruments for home weather stations.
Awesome. Thank you, Ted. Let me just get my screen set up there. Okay. Hopefully everybody can see that. So thank you again, Ted, for that awesome introduction. I'm super happy to be a part of this year. And I, like Ted said, will be sharing some different information about home weather instruments and different options that you can have with your home weather stations, including things you should think through when you're making your decision of what instrument you want, as well as the different costs that different instruments have. So to get us started, I am first going to talk about precipitation gauges. So I've got here three different options that are probably your top three options that you're going to see on your home weather stations that you can get. On the left-hand side, you have your standard rain gauge. These are usually made of plastic and include a funnel at the top that leads to a tube where the water accumulates, and then you take your readings and your measurements. These are pretty easy to maintain since there's no moving parts associated with them, but you can't easily track the rain rates unless you wanted to periodically run out into a storm to take those measurements. So there is a little bit of a limitation there if you're curious about how much rain is accumulating in a certain amount of time. In the middle, we've got a tipping bucket rain gauge. These work by collecting water into buckets that tip once a predetermined amount of water fills it, usually 0.1 or 0.2 millimeters. Each time this tip happens, a switch is flipped and a count is kept, and that's how you actually track your accumulation. These systems do keep track of your rain rates, but they require a little more maintenance because there are moving parts associated with that tipping mechanism. Finally, on the right-hand side is a haptic rain gauge. These are becoming increasingly popular as options for precipitation gauges on home weather stations, and they work by converting vibrations from raindrop impacts on the top of the sensor, and they convert these vibrations from the raindrops into electric signals. So these don't have moving parts, which make them a little easier to maintain, but they are susceptible to some different environmental factors like wind and debris. So the accuracy of these types of sensors can be affected by those different factors. Now, there are some considerations to keep in mind when making your decision on what type of precipitation gauge you want to buy. In general, operational entities with, like the National Weather Service, for instance, require the use of a standard 4 or 8-inch rain gauge for reports to be considered official. This is because not all at-home weather stations are created equally. You're going to have a lot of variance and variability in the quality depending on what types of instruments you get. And these standard rain gauges have been proven in some different tests to be the most reliable and accurate. Another important consideration is whether you have a power source that you can log your data with. A benefit of the tipping bucket and haptic sensors is that you have the ability to have automated measurements, but these do require a power source. So if that isn't available, you're going to have to run into some issues there. And finally, precipitation measurements can be difficult to collect accurately. Lots of environmental factors can affect the accuracy of your measurements. Everything from frozen precipitation, high winds, and even evaporation can cause errors to your measurements. Also, maintaining your equipment is very important as it's easy for bugs and debris, especially, to fall into precipitation gauges or for dust to build up on the top of those haptic sensors, and these will alter your measurements. With all that in mind, some rough estimates for precipitation gauge costs are on the right-hand side here. Your standard rain gauges will be your cheapest option, and an official grade 4-inch range gauge runs about $42. Obviously, you can get non-official gauges that will be significantly cheaper than that. If you want a tipping bucket gauge or a haptic sensor, these are going to vary a lot more in price depending on size and where you get them from. But some of the more popular brands are typically around $200 for a tipping bucket and $100 for a haptic sensor. Next up, we've got temperature. Temperature measurements are such an important piece of weather and climate forecasting. So being able to measure and share your temperature data is an awesome way to have a direct impact with and through citizen science. So it's awesome. First up, we've got your very basic thermometers and temperature sensors. These systems are good for a general idea of temperature and are going to be your cheapest option. They often require no power source or just a few batteries to run on, and they are significantly easier to maintain. However, these are susceptible to direct solar radiation errors that can lead to temperature inaccuracies, so they're best used for more of a general look into temperatures, like if you were curious if it's warm enough to swim outside or something along those lines, but not necessarily the best choice for accurate measurements. For more accurate temperature measurements, it's best to use a temperature sensor that includes a shield. Shields serve a couple of really important purposes, which are to block direct solar radiation on the sensor and to allow airflow over the sensor. The schematic here on the right-hand side shows how these shields work. The sensor probe is located in the middle of the shield, and the shield allows airflow to move over the sensor probe while blocking the direct solar radiation. So it's constantly, as long as there's at least a little wind, aspirating that sensor. The cost estimates, the shields that you can buy for temperature sensors come in a lot of different options, but your two most common are going to be like what you see on the left. The top is just your radiation shield, and the bottom is the radiation shield, plus it includes a fan so that you have constant airflow over your sensor. The cost estimates that I have listed here on this slide, $175 for the radiation and $485 for a fan aspirated shield, are specifically from the Davis brand and Davis Company. And that pricing includes the shields themselves as well as temperature and humidity probes. So while these do cost more, your data will be significantly more accurate. And finally, we have wind measurements. I thought it'd be a good idea to go over some quick facts about wind measurements before getting into different types of sensors. Wind is one of the most variable of all weather measurements, which can make it difficult to measure accurately. Sensors must be able to respond to the lightest of breezes and the strongest of winds. This can be challenging for some instruments like cup anemometers because they will respond quicker to speed ups than slow downs. So if you have a quick gust of wind, your measurement may look like you have a longer gust because that cup anemometer doesn't slow down as fast as it speeds up. Turbulence also adds a challenge to wind measurements. Turbulence itself can lead to rapid changes in both the speed and direction of winds, which the sensor may not have the ability and the time to respond to. And finally, instruments that measure wind typically require a little more maintenance than other types of instruments simply because of all of the moving parts that are associated with them. So now we've gone through some quick facts and we'll get into different instrument options here. Your most common and most cost-effective will be the cup anemometer, which typically includes 3 cups attached to equally spaced arms. You'll often also have a wind vane, like what you see in the top right photo. You've got the cup anemometer on one side and a wind vane on the other, and these together give you both wind speed as well as direction measurements. You can also combine the 2 instruments together into one single instrument, like what you see on the bottom right photo, and that is called an aerovane. These different instruments can be especially susceptible to some environmental factors like winter precipitation, which can freeze the equipment if you have ice, or if it rains and then gets very cold and it freezes the instrument. So it's really important to check your instrumentation periodically. It's pretty obvious when something freezes because all of a sudden it looks like you have no wind. So at least you know something has happened pretty quickly if that were to happen to you. Another option for different wind measurements are sonic anemometers. These operate by using ultrasonic waves and measures the speed and direction based on how sound waves travel between the transducers in different directions. These are simpler to maintain because they don't have moving parts to deal with. They're also a lot more accurate and reliable, especially in weak wind conditions or when you have rapidly changing conditions, again, because you don't have to worry about speeding up and slowing down of moving parts. There are models for both 2-dimensional wind speed measurements as well as 3-dimensional wind speed measurements. 3D wind sonic anemometers are significantly more expensive in the thousands of dollars, so they're kind of outside of the realm of what you would normally see in a home weather station, but if price isn't a matter, it's pretty fun to see updraft winds. Okay, so we've been able to go through some of the different types of instruments that you can choose for your home weather station. So I wanted to wrap up my time by sharing some different all-in-one options that you can choose from. These are great options for folks because you're able to have all your instruments integrated together in one main system rather than having to deal with different instruments and, putting them together and set up separately. So first, I am sharing some different options from Ambient Weather. They provide a wide variety of different systems and cost options as well. So they're a great way to kind of compare between different systems. So their cheapest all-in-one system is $136, and this will measure and take observations of your typical things: temperature, humidity, wind speed and direction, and precipitation. If sonic technology really piques your interest, they also have a sonic station option. The cheapest of those is $370. This is, again, using sonic technology, but also a lot smaller. It's just on, like it looks in the picture, it's just one piece with everything together. And then if you are like, I want something absolutely like really advanced, their most expensive all-in-one option is this $1,300 weather station that runs on solar power, and it includes some additional sensors like optics so that you can take measurements of soil and radiation. So next up, another option that a lot of people turn to is the Tempest sensor option that includes sonic technology and some other additional measurements like a lightning sensor, and it does run off of solar power as well. So just it's very similar in makeup as the ambient weather one, small, but just another option, about the same price, $340. And finally, AccuRite is another common go-to for your at-home weather stations. And they have a cheap option of for $90, that just does wind speed, temperature, and humidity. And so this could be a really good option if you already have a weather station and you have a lot of land and you're just curious, like, hey, how different is it from this point to this point? You could always add this out there for an extra little data point, which could be kind of fun to look at. And then AccuRite also has an all-in-one system for $270 that includes a solar pack as well as some lightning detection as well. So ultimately, you have a lot of different options out there to choose from, and they are going to vary in their sensor capabilities, how accurate they are, how much they cost, things like that. But hopefully now you are able to have a better understanding of some of these different options and feel motivated to collect some data. So with that, thank you all for listening, and I look forward to any questions. And for now, I will pass it back on to Ted.
Okay, thanks very much, Michelle. Yeah, a lot of good insights, a lot of things to consider there. And toward the end of the program, we're actually going to share some links to some weather band content. We did have some of the major instrument suppliers give us webinars about 3 or 4 years ago. And we'll also share that later in the session for those folks that are maybe looking for new equipment or maybe going to start a whole new weather station. And there's just a huge variety of things. It's almost overwhelming. There's such a variety. You can walk into a Lowe's or a Home Depot or a home center store, and they'll have these weather stations that you can buy. And like you said, enormous differences in the quality of what you get there. So we'll talk a little bit more about that. I want to move on now, but I do want to thank Michelle again for her presentation here today to get us started, and then we're going to have some more discussion and some questions around that. I did have one question come up in the chat. Maybe we can talk about that real quickly here. The question was, are there options for weather stations that are accurate and can be connected in apartment buildings? This is
That's a good
something that a lot of
question.
people have. Yeah.
Yeah, that's what I was going to say. That's a great question because a lot of people do live in apartments. I think this would also be a good question to have after the siting presentation because that's going to be your biggest issue is siting is very important for accuracy. So while there are options out there that you could buy that you could put somewhere, depending on your apartment and how much space you have, you may not have the most accurate measurements simply because you don't have the freedom to site it in a good location. So yes, there are options out there, but depending on where you're able to actually put it is whether or not that accuracy is going to be affected.
That's a really good point. Yeah, and even when you're a homeowner, and I think Rich, who's coming up next here, is gonna show us some examples of some of the difficulties of that. So thank you very much again, Michelle. We sure appreciate all of that, and we'll talk more in just a little bit here.
Yeah, thanks.
Our next speaker is going to talk to us about siting, as Michelle referred to, and that's Dr. Richard Clark, and Dr. Clark is a professor of meteorology emeritus at Millersville University, having recently retired after 35 years, 20 years as the department chair. Dr. Clark recently served as the AMS president, and that was actually in 2022. I looked it up. And he presently serves as the vice chair of the Federation Assembly of the American Institute of Physics. His research interests span atmospheric boundary layers and turbulence, air chemistry, and space weather, with a special emphasis on field observations and instrumentation using airborne and balloon-borne platforms. Rich was a PI on an NSF-funded project, Segway, collaborating with NCAR EOL and Comet, that resulted in the creation of 10 modules on atmospheric instrumentation, including site selection for ground-based instruments. And I have looked at that. It's fantastic. Rich is going to be sharing a link for you for that, if for those of you who want to get a little more in-depth. His participation in this session will, of course, focus on selecting a good siting for an instrument setup. And on a personal note, very glad to have Rich here today. He's a great friend and a person that I've worked with on previous webinars, and he's been very helpful and insightful, and certainly glad to have him with us. So, Rich, without further ado, go ahead and take it away.
Okay, thanks, Ted, and thank you to the weather band and the other panelists. Boy, that was really interesting what you had to say, Michelle. I'm looking forward to the further discussion later. Yeah, so a lot of what I'm going to tell you is sort of common sense. Let me just start off by saying, referring to these images that I have on this cover slide. This is the weather center that we have at our university, and it involves a ceilometer and a rain gauge, tipping bucket rain gauge, and precipitation, particle sizers, and three different temperature and humidity measurements and all of that. You'll notice one thing I want to point out right here is notice the surface that we have. It's a grassy surface, and that's something that you want to be thinking about whenever you're putting in a weather center. You might not have the funds to put in something like this. This ran about $60,000 or $70,000. But no matter, if you're buying a $200 weather center, you still want it to be representative. This is just a photograph here of the temperature and wind, and you'll notice that Michelle was talking about sonic anemometry. Here's a sonic anemometer that also has something called a disdrometer that is a piezoelectric sensor underneath here that responds to the acoustic sound of precipitation falling on it. I put the picture of the flags up because this is not a place where you would want to put a wind sensor. You can see that some two flags are blowing one way and the other two are the other way. And nor might you want to have your sensor inside this box as the Ellis, Kansas bank did. But I had coffee with the bank owner, and it was sort of interesting because he said, well, it'll tell you what the temperature is whenever you're walking past the bank and what it feels like. And he had a point there. So let me go on. What's the purpose of this site selection? You want accurate data collection. You want it to be reliable and representative. And I put in reliable here. You might not think that should be a citing issue, but if you cite it better in the sense of accessibility and to your site, the chances are you're going to be able to tend your site more often and ensure that the data is more reliable. But this is the most important thing: representativeness of the site, and that is the site should reflect the broader area's climate conditions. Sometimes you can't do that. The very first question was, what about if you live in an apartment complex? And yeah, that's difficult. I mean, I have a weather center out here. I do my best to put it in a weather station out here, and I do my best to sort of, make it representative, but I still get shade in the early morning that's affecting the temperature that I can't do anything about. So representativeness, accessibility, and safety are the key considerations. Before I go on, first of all, I just want to sort of note that on the right-hand side, the photo that you're seeing there are some students who are putting together a flux tower up near Geneva, New York, in preparation for a study that we did on Ontario winter lake effect systems. But if you have a moment and you want to take an image of these two QR codes, one is to really a fantastic guide for meteorological instruments from the World Meteorological Organization, okay, the WMO. It's all about the standards and everything. It's just full of information. You can download it as a PDF and look at it. And the other is, Ted referred to these modules that we created back in, just before 3 years before the COVID era, but 2016 to 2019, we had an NSF grant. We produced 10 modules on instrumentation. Each one of those talks about representativeness. Some of it goes into aircraft measurements too, so that might not be of direct relevance to this talk because you're interested in ground-based, but mostly there's a lot of ground-based instrumentation in these modules, and you have to register for it, but they're free, and because they've been paid for already by the taxpayer through NSF. So I encourage you to go into those. And then Rick and Halteman is going at the very end is going to post some web links to the manufacturers' websites where instruments can be purchased. So there's environmental and geographical factors to consider. Like I said, a lot of this is common sense. You know, you want flat, open areas, avoid being too close to obstructions, trees, buildings, and all of that, because you want accurate wind and temperature measurements. You want to avoid things that aren't representative of your area, and unless they are. You know, some people may want to put a temperature measurement in a valley because they want to see some, you know, the cooling, you know, the cold pools of air or something like that. But generally, you're going to want to avoid anything that is too much of a gradient, you know, or obviously prone to flooding for obvious reasons. Vegetation and obstructions, you don't want to be near trees, buildings, and all of that. Typically, this is sort of the rule of thumb right there. Whoops, I'm sorry. Let me go back. 4 times the height of the obstruction is a good distance to be away. So if you have a tree 30 feet tall and it's going to be in your way, you move it, try to keep your weather station, you know, 120 feet away. The grass or low vegetation, as I showed you in that first slide, is generally preferred to minimize the heat effects. If you go too close to bodies of water, now sometimes you might not have a choice, but if you're too close to bodies of water, you're going to pick up that humidity. And that humidity, it's going to affect your humidity and temperature readings because there's more moisture in the air routinely close to those bodies of water. And of course, everybody has heard of the urban heat islands. You want to avoid those areas like the Ellis Bank and its 111-degree temperatures, whenever actually, by the way, the temperature that day in the shade was 98 degrees, the official temperature. So all of those things are pretty much common sense, right? So instrument specifications and maintenance, you know, Michelle talked a lot about the instruments, but in terms of representativeness, you know, you want to be able to, if your instrument is going to be remote and you're going to be collecting this data via some data transmission, like putting the data into the cloud where you access the cloud, or just some radio signal into your digital display in your house, you're going to need some power and connectivity. So that's an issue that you're going to have to deal with. How far away, you know, can you do that? You want to be in a place where you can do some maintenance, regular maintenance and calibration of the instruments. I mean, and by the way, there's a lot of this information in WMO guidelines, but you want to be out there. I find in my area, I especially I go out with a dusting wand occasionally and just sort of dust it off, clean it if I have to, but oftentimes just try to keep the spider webs from getting into the radiation shields or the temperature and humidity gauges. And then future proofing, you know, I don't know if this is so important, but you know, if you're expecting land use changes in the region of over a short period of time after you install, well, that might be a consideration. So I'm going to talk about specific measurements. The site specifications related to measurement types, location, again, open areas away from buildings and pavement and artificial heat source. Over grassy areas is the best. The temperature measurement should be between 1.25 and 2 meters above the ground. 2 meters, I guess, is generally considered the standard, although WMO, World Meteorological Organization, allows this range of heights. You have the ground surface should be, you know, not near concrete or asphalt. Anything that has different heat retention characteristics than your general area. Ventilation, be sure, and Michelle mentioned this before, and showed a diagram of the ventilation around the sensor. Whenever you're looking at these sensors here, you see these the radiation shields, and you want to have your temperature probe, which is comes up right here through the center of the radiation shield. You want this to be in an area where there's free flow of air around it for ventilation. And then shielding, you either have something like this if you're going to put your temperature out there, or a Stevenson screen a Stevenson shelter, which is, you've seen these wooden boxes, oftentimes wooden boxes painted meteorological white. Actually, there's a paint called meteorological white, and a highly reflective paint. And you can put your temperature, your thermometers inside there. Humidity measurements. Humidity is a tough one. You know, it's hard to get good humidity measurements, but there's some important considerations. One is, again, the bodies of water. If you're too close to large bodies of water where there's lots of water vapor in the air, your humidity measurements are going to be biased. Ventilation, you want, again, just like the temperature and humidity sensor is inside this radiation shield that you see. And it's for that. There's a couple of reasons for that. One is it's ventilated, and the other is this third bullet here: temperature considerations. Relative humidity, you have to understand, is a ratio between the actual amount of water vapor in the air and the amount of water vapor that the air can hold at a given temperature. So the denominator of the relative humidity ratio is a direct function, actually a really strong function of temperature. So it's really important that you have your temperature probe in the vicinity of your humidity probe. And most of these, fortunately, their temperature and humidity sensors are co-located for most weather stations. So measurement type, precipitation. Here I have a couple pictures. First of all, the height of your rain gauge should be 1 meter. This is a WMO standard. The obstructions, you know, more than 4 times an obstruction height. It should be open to the sky, and it should be horizontal and free from splashing. If you look at the top of this slide, you'll see there's an alter. This is called an alter type shield that sort of slows down the wind as it approaches the tipping bucket rain gauge inside. If you can, something like this, you can actually make something like this, but that's optimum to be able to bring the wind down to a slower speed, so you don't get gusts moving across the surface of your wind of your precipitation measurement. And then over here, I just included a snowfall measurement. If you're trying to measure snowfall, these are called snowboards, and it can be either 16 inches or 2 feet square, and it's just a pole. Oftentimes you put a piece of tape on the top here, like they have right here. And what you want to do is you want to locate it in a place that is sort of representative. You'll notice that this is located sort of in a semi-forested area that where that forest tends to slow down the wind, which is a good thing, but you don't want the snow coming off the trees and dumping onto your board. And the board, and this pole here, by the way, can be graduated. That is, it can have measurements on it, but that's typically not the best. It's typically better to have your own ruler and just sort of stick it down, at various locations around this plate, and take the measurements at several locations. But if you have this located far enough away from the trees, but yet in the trees, that's really sort of an optimum. This snowboard here is located in a pretty optimum place. Wind speed and wind direction. When your anemometer should be 10 meters, recommended is 10 meters above the ground. It's like 30 feet above the ground. You want to be 10 times farther than the nearest obstruction. Your exposure, you should be, atop structures or open, position on open terrain, and you want it to be non-vibrating and a stable mount. For instance, this image that you see here on the right, these are welded pieces of steel that hold this steady. Now, the reason I put this up there is not because it's the right thing to do. It's because it's actually not the best thing to do. This is on the 4th floor of a building. This portion here that you see is on the 4th floor of the building. We have this at Millersville, and this is where our wind sensor is. And you may say, well, why did you choose it there? Because there wasn't any other place around in our entire area where we could get representative wind, and we have a legacy. We have historical measurements that go back decades of wind measurements that were taken right here. So rather than put it somewhere else where we were going to have to deal with obstructions anyway, we put it on top of the building, and that's what you see there. So yeah, there's that consideration. And then I think this might be my last slide. Air pressure measurement, again, well ventilated shelters to minimize temperature variations, but you don't want it to you don't want it to be in a situation where you want to be able you want it to keep away from vents and open windows and HVAC systems that influence the pressure reading. You've all, if you've ever, if you have a door that opens up into a garage, say, and your garage doors are closed, and you try to close that door, you know how oftentimes the door won't close because as that door is closing, it's building up pressure inside the garage, it's preventing it from closing. So you don't want to invoke any kind of dynamic pressure into your pressure sensor. And the reason why temperature is important is because these pressure sensors are capacitance sensors, and the capacitance is measured by the two capacitors and how far they are apart, and temperature affects that distance. So you have to be careful of that. And then finally, solar radiation. Obviously, you want an unobstructed sky view. Here's our our radiometer on the system down at Millersville, and this is pointing due south. It points due south because we don't want anything shading it. So you want an unobstructed sky view. You want stability. You want to make sure it's clean. This is a high quality glass, and it measures allows for the transmission of radiation between like 0.28 microns and 3 microns. So from near ultraviolet to infrared. You want to clean it regularly, and you want to calibrate it occasionally. And what happens is sometimes you don't have a choice. Here's a situation where there's a weather station, and it was the only place that this person can put it. And every now and then, or once a day, under sunny skies, this tree is going to shade that, and you're going to see something that a dip in the solar radiation curve. So it's just things, that's the problem with sighting is sometimes obstacles and obstructions are unavoidable. Anyway, I think that's my last slide, and I'll stop here. Ted, thank you. I hope I was not too far on time.
No, that's okay. Thanks very much, Rich. Thank you for all of that. Good insights and a lot of things to think about there. And I'll try to move on quickly here. Time flies when you're having fun. We're really getting into this, and that's great. But I want to make sure we try to leave some time toward the end for some questions. We do have a couple that are coming in. So let's go on to our next presentation, which is by John Horrell. John is a professor of atmospheric sciences at the University of Utah. Dr. Horrell has been involved in research and software development related to providing access to environmental observations for observational research and educational applications for decades. This research and development is applied to many societal issues, including public safety, fire weather, flash flooding, and air quality. The research and development undertaken initially by the MesoWest team in his group led to the development of a public benefit corporation, Synoptic Data, whose mission is to provide expanded access to environmental data to enhance public safety, improve the productivity of government agencies and commercial entities, and assist in research and educational initiatives to advance the understanding of Earth systems. So very glad to have you with us today, John. Welcome, and please go ahead, help us navigate this world of sharing our data from our weather stations.
All right. Yeah, thanks, Ted, and thanks to Michelle and Rich for kicking this off. My part of this is, if you have a weather station out there, how can you get that information from the weather sensors moving around and available for others? And then the question is sort of, well, why? I mean, obviously, if the individual puts out the weather station, they have a good reason for it. They want to know what's going on there. And it's awesome, the companies now that are making the instrumentation to make it both affordable and really easy to have it available for personal use, but then often to be able to share that information. So obviously, it's really useful to be able to see how observations from a station might compare to those that are around and nearby. And it helps to be able to quality control your data as well as what those other stations are like. And I take a little bit of a different attitude. I mean, from on the national scale, it's really important that we have the information from good sensors to be able to give us information. On the local scale, there's a lot of representativeness issues that it's tough for the to be able to deal with, particularly in the West where I am, and I'll give you some examples of that. So there are a lot of local variations that are critical, actually. So whether you're in an urban area, suburban, rural, wherever, it helps to have information from that area. One of the other things is that sometimes just because the way other information systems share, provide the information, your station may be something that has a communication protocol that others don't have, and you may be the only one that is being able to share that information. So certainly a critical thing, if your information is getting out there, especially to the National Weather Service, it's going to assist in public safety and actually help validate watches and warnings that the National Weather Service may issue, as well as these many other things. I did want to take a moment and just mention the severe impacts on individuals in the federal agencies, including the National Weather Service, that have been fired recently. If these actions aren't reversed, there is a real potential for detrimental effects on public safety and so many impacts of the work that's been being done by these federal employees on society. So this is a real tough time right now. So how are you going to move the bits and bytes around? Well, there's thousands of these personal weather stations out there, the kind of all-in-ones that both Michelle and Rich talked about, and you have personal displays, and I can look at my weather station, on my phone, but you're working with a vendor. The vendor that sells the station is usually going to have a communication protocol where they're going to either go and grab it from your site or you're going to push it to them. And then they're going to have ways to be able to display that as well. And that's usually typically part of purchasing a station is, well, how is that information going to flow? But then the vendor may also then send on to aggregators, other groups that take the information and then make it more widely available. And there's lots of these kind of aggregator systems. Not every vendor may share it. It's kind of up to their business model. And then whether those vendors directly or through other aggregator hubs, that the volume is sort of increasing as you see the thin arrows up to the big arrows. Is it going to be available for Weather Service operations and services and displays? So how do you go about doing this? Up here on the top, they'll be kind of moving along the different pieces of this sort of chain. And the first thing is look at your manual or the information online on what the manufacturer allows as far as what the personal use is, and then how the vendor may describe the license agreement that when you purchase a station, that they maintain the rights to the data as well. And then whether the vendor permits the data to be sent on to an aggregator, such as Weather Underground or the Citizen Weather Observing Program that I'll talk about. So vendor networks, Earth Networks, Davis, Tempest, there's many out there that make these services available, and it's fantastic. The data aggregators, Weather Underground's been around a long time. Citizen Weather Observer Program has as well. It started from ham radio operators, and then Synoptic that Ted mentioned here, and you'll see a couple of examples from. So the Citizen Weather Observer Program, something that Synoptic helps facilitate, as well as there's other, the NOAA and the National Weather Service help support, as well as many volunteers. So there's about 13,000 stations across the the country that are, basically these home systems that are available and then disseminated around. Synoptic has access to hundreds of networks, and so there's nearly 80,000 stations in the public domain that are available through Synoptic. Just look at 12 seconds of data flowing around the country. So these are all different kinds of data streams that are coming in, and literally that's real time. That was 12 seconds. So I have a weather station on a second home that's in a very rural area in southern Utah. And how do my bits and bytes move along? Well, Ambient that Michelle mentioned supports transmission of the data to the Citizen Weather Observer Program, and there's kind of a separate entity, Ambient CWAP, that then helps to push that data along. So, which is really nice. And so that can be looked at in time series formats. And this just happens to be my station, and it actually gets into the hazard viewer for the National Weather Service through CWAP. And so this is where that station is. And I dropped a few slides along here so you don't have really any context. This is southern Utah, but this is near Zion National Park. And there's millions of visitors that are traveling on this road between Zion and up here to other national parks, including Bryce Canyon. And so having additional information in this area is really useful for the National Weather Service. So for you, if you have a weather station and you're interested, you can always send questions to me. I can help answer some of the information or push those along to others who can. But review your options as far as what you're allowed to do to share your data from your station. Look at the ways that you can display the data and see it through other manufacturers' web displays. You can go to all their sites and they'll have public exposure of what's available. Weather Underground, the Weather Service Hazard Viewer that gets its data from Synoptic, and then follow through and get your bits and bytes moving. And Michelle mentioned, there's still a place for manual observations through the co-op program, COCO RAWS, and MPing. So, lots of ways to be involved. So with that, I think I'll turn it back to Ted.
Okay, thanks. Thank you very much, John. Great presentation there to give us some good picture. I know it gave me a good picture of how all that system works, and I've just started getting into that sharing part now myself in this last week or so. Got onto the CWAP network and never tried to do that before. I've been part of the Weather Underground, and so it took about a week to get it all running and working. So it's kind of exciting, and I think it's a good thing. I think it's great that people are sharing and that we have these services that are aggregating the data. Before I forget, I do want to recognize my partner in this, who's working in the background helping. Someone mentioned him earlier, and that's Rick Halterman. Rick's been a great partner in organizing this session, and also he's taking your questions and moving those over to us. So that's what we want to get into now. So thank you, Rick, for all your work on this. And I want to try to maybe take a couple of those questions. One of them was on, it's kind of interesting on Wi-Fi and locating the station relative to Wi-Fi. Sometimes maybe that can limit how we position our instruments because we have to get to a Wi-Fi router, for example. Any thoughts on that from the panelists here? I'll just throw it out to you.
Yeah, I can comment because I think it was related to ambient too. And yeah, that's an issue there. I mean, a lot of it is those pragmatic decisions about where you have power, where your router is. If you have options to be able to put another booster out there somewhere closer to your station, that can help. But yeah, it's definitely an issue, and it's going to depend. You can try putting your router in different spots in the around the house to the extent that you can do that. away from wherever you're kind of plugged in.
Yeah, that's what the option I chose, John, was I took a booster, and I have an outside outlet that was closest to my weather center, my weather station, and just plugged it in, and that helped.
Okay. Great. Good advice. Some things to try there. We have another question here. My station only allows me to export data within the past year, so this is kind of a data-oriented question. Has anyone encountered this and figured out a way around it, other than making sure we download our data periodically and save it? So, wanting to preserve data without having to manually keep up with that.
Yeah, and I can comment a little bit. Yeah, I mean that's part of the agreement that a manufacturer of the sensor and whoever's distributing it will have in their agreement with you. So it's one of those things of all that fine type. Sometimes you do need to read all that fine type to know what are the do's and don'ts. Um, that's why if it and it's also the differences between different aggregators as far as access to the information, down the road. I do have, one thing that's tough is, it's a lot easier to deal with data in quasi real time than try to extricate it out later. So yes, either, if this is something of interest to you, you should try to download your own data or check with the, upstream through the various data aggregator steps as far as what the policies are.
Okay. All right, great. I had a few questions that we prepared here, and thought maybe we've got just a little bit of time left, and maybe we could go through a couple of these. Um, we talked. I think Michelle talked a little bit about the haptic type sensors. How accurate are those for rain rates, and how are they affected by other things like ice and snow and that sort of? I think about ice and snow because I'm here in Minneapolis area.
Yeah, so they vary quite a lot depending on the where you buy your sensor from. Ice and snow, things like that are going to be a lot different than rain. They're still kind of new-ish in terms of an instrument source. So different companies are trying to change their algorithms so to handle things like frozen precipitation better. But the accuracy can range quite a lot, depending on things like your wind speed, and other factors like winter precipitation. That vibration is going to be, that it picks up is going to be different than what you would get from like a raindrop, a liquid raindrop. So I don't have like set specifics in my head. I don't know if the others can chime in on that, but it varies quite a lot from everything that I've seen from different companies.
Yeah, I have an acoustic disdrometer here, and it doesn't do well, and it's a pretty high grade one. But it does not do well for light precipitation. I primarily, although it's intended for precipitation and tendency, it doesn't do well for accumulation. You know, it doesn't get the rates right. What I like about it is if there is moderate drop sizes, it'll pick those up and it'll give me a good accurate time for the onset of rain. But if it's drizzle, forget it.
Okay, well, we're almost out of time here. Thank you again, everyone. I was going to ask my partner Rick also that to put in those links. We had a few weather band webinars from several years ago that really surveyed a lot of the instruments that are available out on the market, and that might be helpful. to some of the folks. So Rick will put those in the Q&A so that you can look at those. And I know we always seem to run out of time. There's always more to talk about with these things than we have time for. But a great session. Thank you very much to all three of you for taking your time to talk to us about these things. I think it's a great start, and we can continue some of this discussion also in the weather band and open AMS community for those that want to do that. If we can always post some questions offline and post some of that in the AMS community for those that think of things afterwards. So once again, thanks very much. Great session, everyone. And thanks everyone out there for joining. Gideon.
Yes, Ted, thank you so much. John, Michelle, and Rich, thank you for taking the time and putting the work into bringing this to our community. This brings our Getting the Most from Your Home Weather Station webinar to a close. Our very last webinar for this year's Jamposium is coming up, so stay tuned. It is Light and Air, Understanding and Appreciating Atmospheric Optics, coming up at 2:30 p.m. Eastern Time. See you there, and goodbye, everybody.
Bye, everyone.